start with the lecture today. How many of you have been watching some of the lectures that have been posted to YouTube? That's more of you than I expected, actually. So, how are you finding them? Pretty good. I get some yes, no's, yeah. Anything, is there anything anybody could suggest that we might be able to do to improve them? No, not really? I wish I could do something about the fan in this room. I think right now, probably one of the things that's least good about the videos that are going up online is the sort of background noise. And, you know, a certain amount of that is actually just people talking in the room. But I'd say in this room particularly, a fair amount of that is contributed to by the ventilation system. So, unfortunately, there's not really much I can do about that one. If you compare the other lectures that I've been putting online from the other class, you know, just give them a listen for a moment. The speech is much more clear because the room is a lot more quiet. Yeah, there's nothing I can do about that one, but there might be, you know, if anybody has any suggestions, I would have been interested to hear. Yeah. Okay, well, we might as well get right into it then, shall we? So, last time we were discussing recursion. We developed the famous Fibonacci example, an example of a recursive program that is not very efficient until you do stuff to it to make it more efficient. Does anybody remember why the Fibonacci function is inefficient? Yes?
You have to recalculate a bunch of times.
You have to do a bunch of recalculations, which, as it turned out, weren't very useful. Absolutely. So, there's sort of also a structural problem going on inside of this algorithm. Oh, I should dim the lights, eh? Yeah. That's good. That's better. That's best. There we go. Much better, right? So there's a structural problem going on inside of the Fibonacci algorithm. In order to calculate the Fibonacci number of any particular number, we need to know the Fibonacci, two other Fibonacci numbers which are in the sequence. In order to recursively get those values, each one of them also has to know two other Fibonacci numbers. If these function calls are not in communication with each other with respect to intermediate results, essentially what you end up with is a situation where a very, very large number of function calls are being computed. They're not sharing information, so many, many times the same calculations are being run, and you can save a lot of time if you cache your results. So, for example, this Fib40, to calculate the 40th Fibonacci number, would actually take less time to do by hand than to do with a computer if you're quick with your arithmetic. And that's kind of like, you know, generally speaking, we like to keep it such that the computers are better at doing arithmetic than we are. So, yeah. Any questions about that so far? Yeah.
Will an exam question require us to use some form of like capture?
Possibly, yes. I have asked questions in the past requiring the memoization of recursive functions. Sometimes that's a valid test question. Normally I make that like the bonus question. Like that's how I like to split it. It's like implement the algorithm is like the part one, and then part two is a bonus, and like memoize it is the part two. But yeah, so yes, memoization is something that is testable in that respect. Any other questions? Okay. So, slide where we left off. We didn't really get much time to discuss it. So, because ostensibly a fair number of you people are scientists, and if you're not scientists, you should at least have some degree of interest in the objective arts, because otherwise why would you be taking a class on computers? So the question that a scientist should always ask is, if we are going to measure something, what are we measuring and how is it relevant, right? Clearly, algorithms require measurement in order to be compared to other algorithms, right? So the mechanisms by which we generally measure algorithms are presented on this slide. Now, it needs to be stated with with a fair amount of force. You can't just run the algorithm on your laptop and say, okay, it takes that amount of time, that's good enough, right? There are as many different types of computers and computing devices now as like the population of a small country, or possibly the population of a large country. There are many computational devices out there. Each one of them has different characteristics with respect to the architecture with which it's set up, the amount of resources it has available to it, all kinds of different stuff. Like, if you look around this room, I would be surprised if there were, excluding Mac users, I'd be surprised if there was more than 3 duplicate laptop makes in this room right now, you know? So, the way that this interferes with things, it's like, okay, so you know how long an algorithm takes on your computer. What can you say that generalizes to everyone else's computer? Because in theory, like, the information about how an algorithm runs on your computer is next to useless when you're trying to determine the general runnability of an algorithm or something like that. So in general, we try to stabilize the idea of the efficiency of an algorithm around a couple of metrics, right? So one of the biggest ones is runtime complexity. So sort of regardless of as to how fast your processor is or how much memory it has or any of those considerations, in general, the amount of time that it takes an algorithm to process inputs has some mathematical relation to the size of those inputs. Now, size may vary. This is something that is, it's one thing in some contexts, it's other things in other contexts. But, like for example, in the Fibonacci algorithm that we gave, what size of the input translates to in that respect is the size of the actual integer. That is to say, the magnitude of the integer that goes into the program. A lot of the time, what we mean when we say size is we mean the number of elements in a list, or the number of characters in a string, the size of a data structure. Most of the time, when you operate a computer algorithm, there's going to be some kind of data structure of non-specific size involved, unless you're doing like trite little mathematical examples, such as the Fibonacci sequence. So that's normally the size of input that these metrics refer to. With me so far? So while the actual runtime on any particular computer will vary greatly by computer, this relationship between the runtime and the size of the input that you put in, that will remain relatively constant. And the reason that that remains relatively constant is because it's not determined by how fast the computer processes your algorithm, but in general, the structure of the algorithm itself. it comes down to things like how many loops do you use? What is the degree of nestedness of the loops that you are using in your algorithm? How is the recursion structure? Is it a bad recursion, like in our original Fibonacci, where each input, basically, the runtime was proportional to 2 to the power of the number that we put into that thing, which is bad. You can have other algorithms, some of which we're going to examine in this class, where the amount of runtime is proportional to the base 2 logarithm of the number that you put into it. So, if this is like the size of the input, and this is runtime, you haven't, like, for those of you in the know, I'm talking about big O notation. We're going to get there. So in some cases, the amount of time it takes to run the algorithm is directly proportional to the amount that you have to process. These are so-called linear time algorithms, right? We call them big O to the big O of n, right? So linear search is an example of a linear algorithm, oddly enough. With linear search, you have, in order to guarantee that you found the element you're looking for, you have to look through every single element in the data structure. So you have to do something once for each element in the data structure. That means it's a linear algorithm, right? Regardless of how many statements there are inside of the loop, right? It's not the number of statements inside the loop that matter. That's going to affect the overall runtime for sure, but it doesn't affect this proportionality, right? It's the loop itself and the number of iterations that loop has to go through. That affects this guy right here. So, for example, linear search uses like a for loop, one for loop, right? It does stuff. If we have an algorithm which has to loop over the data structure twice, that is, it's a nested loop, right? So, for I in some list, then for j in the same list, right? Looping twice over the same data structure. If you have an algorithm that does that, how many times does this inner loop run? Any ideas? Yes, sir.
Each time, like the outer loop?
What? Yeah. So, sorry.
Like it runs for each thing in the string or whatever?
Yeah.
Multiple times because the other loop is
Yeah, so if we have some statement here, x equals 3, right? This loop loops once for every element in L. Then this, which is what you're getting at, this whole thing loops once for every element in L. So this is a multiplicative factor. The number of times that this statement is executed is proportional to the square of the number of elements in L. If we are considering that to be our input, then an algorithm with this structure is proportional to a parabolic function, specifically n squared. Right? Question?
Are the axes supposed to be flipped?
Yes.
Okay.
Bloody hell. Thank you. How embarrassing. Everything else I said is fine, though.
Yeah.
Any questions about this so far? So, you can see the pattern there, right? If I were to put another loop inside of that loop that was iterating over the same number of items, I would end up with something that grows even faster, n cubed. cubed, right? The Fibonacci number, yes?
So for every extra nested for loop, it adds another exponent.
Yes. Yeah. Because, like, for A and L, this guy runs the size of L, right? For this guy. This loop runs a number of times equal to the size of L, right? So from here, it runs length of L times. This gets run length of L times. So you multiply them. This gets run length of L times. So you multiply them. So, yeah.
Because L is the same size, and that's why. Okay.
Yeah. And we're actually going to get into some examples a little later in the course that have precisely this structure. It's going to be a search algorithm which finds perfect Pythagorean triangles. Our first attempt at that actually does require a triple nested loop, so these things don't exist. These aren't just academic cases, so to speak. So those are, like, not great but manageable. The for loop instance is like zoom. Very, very bad, because it's 2 to the power of n. It increases very, very quickly proportionally to n, right? That's why I could enter a number like 40 and it would take like a minute to process. On the other side of things, you have logarithmic functions, right? Well, you also occasionally get square root. If your algorithm is proportional to the square root of n, which occasionally happens, it's not super common, but it does happen, you're doing better than linear time. If you've got a logarithmic function, big O log n, notice I omit the O because this is the base 2 logarithm. That's equal to log base 2 of n. That does still better. So basically the object of algorithms research in general is to try to push algorithms that are in this range down to better and better better functions. Does that make sense? Yeah. And, again, there are structural reasons inside of the algorithms that cause proportionality to these functions. It's not dependent on the hardware that you're running, right? So that's essentially the idea of runtime complexity. You'll hear this, especially if you go on with computer science courses. You'll hear this referred to a number of different ways by different people. Sometimes it's called runtime complexity. Sometimes it's just called big O, right? Often they'll refer to quote unquote a linear algorithm, an exponential algorithm, a logarithmic algorithm. Sometimes they'll just kind of omit the idea that what they're actually talking about is an algorithm at all. So if you hear someone speak about an algorithm and then attach to that the idea of a mathematical function, in the absence of any other context, you can probably assume that unless that mathematical function is directly related to the operation of the algorithm itself, they're probably talking about runtime complexity. Make sense? So what's talked about is memory complexity. Essentially the same idea here, but it's how much memory the algorithm will consume based on the input that it's given. A lot of the time, the amount of memory that your function consumes will often be either linear or constant. There's one that I forgot to mention here. The absolute best case scenario of all is constancy. big O of 1. So, yeah. Oh. Is that so? I haven't touched my computer in that long. There. So, memory complexity is a very similar idea. So our original implementation of the Fibonacci algorithm, while it, you can make the argument that the occupation of the call stack by that algorithm constitutes memory usage, but if you think about just the declared variables, it didn't have it. So its memory usage was constant. It only required as much as its instructions. And then the operating system took care of the actual execution, which of course did require memory, but everything requires memory. Some algorithms, so when we modified it to include the memo, we are now occupying essentially one cell of memory for each possible input to this function. So, essentially, we were able to go from a big O, we were able to go from this guy right here in terms of runtime complexity to this guy by going from this guy to this guy, right? Which is a good deal, because this is a killer, right? As we demonstrate. Is this making sense? Good. So, so that's kind of like the theoretical angle on things. Practically speaking, of course, all of this theoretical mumbo jumbo doesn't actually make any difference if it's not reflected in the actual runtimes and memory usages as measured by the computer, right? So, there are various ways that you can use to time the efficiency of algorithms. It's really kind of more of a subject. 1xc3 gets into it a little bit, again, if I'm teaching it. You can use other programs to analyze the execution of programs. This is called profiling. This can get you a good view into the memory usage of particular functions inside of a program. And it's quite easy to time programs, at least in a Unix environment, because there's a time command that essentially acts like a stopwatch. And it's, you just say time and then whatever command you want to enter, and it times the command as I demonstrated last lecture. So yeah, moving right along. So, practical runtimes of the recursive Fibonacci algorithm. Again, the actual runtimes aren't important here. What's important is the relationship between the value of n and the amount of time it takes to execute. You may notice that each 5 that we go up, we are on, within a certain tolerance, but we are essentially multiplying the amount of time it takes to execute by a factor of 10. So we're not quite hitting an exact 2 to the n. This is, this has to do, again, with the manner in which, okay. Would it be useful to you guys if I got a little bit more fine-grained and a little more detailed on big O? It's a really useful concept that basically you're going to be expected to know without anybody really teaching it to you. So this might strike you, some of you good people, as an odd way to write something like this. It's like, well, it's a proportionality to n squared. Certainly there are other factors, right? So, yes, there are other factors. So, in reality, when you measure runtimes like this, you'll derive something like you'll derive a formula that's something like an squared plus bn plus c for some constants a, b, and c, right? Generally speaking, big O is a simplification of this. There may even be other like factors sort of snuck in there, like maybe there's an n, well, that's square root, so I'll just use square root. Maybe there's c times n square root of n. Maybe there's like even d times log base 2 of n plus some constant e, right? The approximation that is being made that characterizes a formula like this as being an n squared algorithm is the asking of the following question. Imagine we take the limit of this as n approaches infinity. Which one of these terms determines what the overall value is going to, which one of these terms will contribute most to the runtime at large values of n, right? Yes?
The one with the highest exponent.
The one with the highest exponent, absolutely. So in this case, it's a times n to the power of 2. So essentially, the first step that big O makes is it excludes everything except the highest power, right? And obviously, I'm not sure if you would consider 2 to the power of n to be a power of n, because it's not really, but it's still much larger than it. So whatever the biggest thing is, the biggest thing rules the roost. So the next question is, what is the nature of this coefficient? And why do we not include that coefficient when we talk about big N, or big O numbers in general, right? Well, it turns out that all of those specific computer specific details that I was talking about that cause computers to run programs at different rates, all of that has been packed into that coefficient, right? So, roughly speaking, A is the amount of time it takes to execute whatever is on the innermost part of the loop, right? B is however much time it takes to execute anything that's sort of at the level lower than that, right? So essentially, because that's implementation dependent, we don't talk about it when we are sort of generally characterizing the algorithm. We kind of just say, yeah, we won't talk about that either. We'll just take the highest power. Does that make sense? That's kind of like the logic behind it. You should think of big O notation not so much as a precise mathematical relationship between the input and the runtime. You should think of it as a manner of categorizing algorithms, because that's how it's used. It's a way of categorizing algorithms. Basically, it's a way for computer scientists to brag to each other, oh, you know the arbitrary search method using cheese and my left toe, I managed to get it down to n times log n. It's like, oh, n times log n, we must show you the proof for this sometime. That's kind of how it goes. I don't know why they're all British. Actually, I do know why they're all British, because the British did a lot of the theoretical background work on computer science in general, because, you know, Turing and Church were all British and all that stuff. The British, early 20th century British really were like just on top of the stuff. So yeah, runtime scales exponentially with n, we've covered that. We have actually already implemented the memoization, and we've talked about it sufficiently, I think. Yes, yes, yes. Runtimes with memoization, absolutely. runtime scales linearly with n, which is efficient for even large n. So, yeah. I'll just make like one more point about this, right? Logarithmic algorithms are extremely, extremely good, right? With a logarithmic algorithm, you can literally process millions and millions of data, of inputs in, you know, maybe 100 steps. Like, it's extremely powerful. Logarithmic algorithms are extremely powerful. And if not for logarithmic algorithms, all of the data processing and the big data stuff that makes the internet work and all of that kind of stuff would take longer than human lifetimes to actually process. So, so it's not like this stuff is trivial. Make sense? Cool. All right. So let's shift gears a little bit and talk about searching algorithms now that we've had a good jaw about algorithms in general. So, did we? Yeah. We mentioned linear search at one point. Anyway, so search algorithms. This is a category of algorithm which is like very, very, whenever you take computer science courses, no matter what the institution, they'll probably start you off with either searching or sorting algorithms. So we're going to talk about searching algorithms. So let's say you had a data structure. It may be pertinent to you to know whether or not some piece of information is in that data structure or not. Let's just say that you had a database which had transaction records, and you wanted to pull out all of the transaction records that happened within 2 hours on a particular day. That's a searching algorithm, right? So, here's the question, right? And I kind of already gave away this answer. How many of these items do you have to check to make sure that you have correctly determined whether or not something is in that data structure or not? Yes?
Everything that's in the data structure.
Yes, you have to check every single one. So, the element that you're looking for might be hiding in the last place that you look. It's kind of like your keys. You know how your keys are always in the last place that you look? That's what data structures are, right? And because it's computers, that's happening several million times per second. So, the reason that we have to check every single element is because we do not have any structure imposed on this data on the data just yet. We're going to get there. So essentially, if you want to just search through a data structure to see if something is there or not, you could just say return E in L. But this is what in is doing behind the scenes, right? Like Python has this interesting little habit of, hiding entire gigantic loop structures behind little tiny words that aren't even functions. So, for I in range from 0 to the length of L, if L of I is equal to the element we are looking for, return true, otherwise return false. Quite simple, right? So, this kind of gets into one of the highly fundamental aspects of computer programming that's kind of introduces itself at a beginner / intermediate level and never leaves you for the rest of your time computing. If you can make assertions, assumptions, or if you have information about the data, you can use that information to construct a more efficient algorithm. So in this case, while it is true that if the data is random, we have to check every single element. If the data is not random, we do not have to check every single element. One very important property of data, which can be established via sorting algorithms, is the property of sortedness. So, if I have 7, 3, 9, 2, unsorted data. If I have 2, 3, 7, 9, sorted in ascending order, right? I realize that's a basic definition, but it's an important one. So when I say when I'm talking about the sortedness of a data structure, this is what I mean. If I'm talking about preserving the sortedness of a data structure, I am talking about modifying it in such a way that each element in it is less than all of the elements that follow it, less than or equal to. Make sense? So, this is a very cool algorithm, right? We're going to talk about an algorithm called the binary search algorithm. And I kind of want to just do it on the board, actually, because it's kind of like animated. So I'm going to do that. I'm the professor, I get to say. Here we go. Hi. And retract. Where's the retract button? Up, down. There we go. Cool. All right. Question?
Does it have to be ascending order?
It doesn't have to be ascending order, but whether or not it's in ascending or descending order will affect how it'll affect how your algorithm is. Like your algorithm needs to assume either ascending or descending in order to work, right? But basically the algorithm for descending is the same as the one for ascending, but like with things swapped around. Yeah, it's like the mirror image, right? So let's assume. Oh my God! It's like, did somebody shoot the screen or something? It's amazing. All right, I'm not using the cursed Blackboard then. I don't want to give you cursed information. All right, so let's assume we had a data structure, right? 1, 3. I'm going to put bars between them, all right? 7, 11, 23, 42, 83, 99, 100. Here's a data structure. Let's imagine that we are searching for the element 64. So does this exist in the data structure? The computer can't know that without looking, right? As human beings, one of the great advantages and privileges that we have over computers is that we have eyes, right? We can look at the numbers and we can look at them all at once and just determine that's not in there, right? But a computer doesn't have eyes. It can only look at one memory cell at a time because that's how a Turing machine works, right? That's how a processor works. It can only process one data element at a time. So it can't see the whole thing simultaneously like we can. So, this is the binary search algorithm. You take a look at your data structure. You pick something sort of, I would say, in the middle. So let's see, we got 1, 2, 3, 4, 5, 6, 7, 8, 9 elements. So this is the middle element. Is this number equal to 64?
No.
Absolutely not. Is it greater than or less than? 23 is less than 64. Yeah. So, because we know that this number is not 64 itself and is less than 64, we know for a fact that if this number exists, it must exist in this half of the algorithm, this half of the data structure, right? So we can, in effect, exclude all of these possibilities, right? So we now have a sub-problem of the same problem, right? And I'm going to do this in a different color. Green on green chalkboard, that doesn't seem wise. Blue, there we go. So, we take a number which is in the middle-ish. If it's an even number, then you have to pick like on one side or the other. So let's pick here. Is 83, actually, you know what, I'll just write it out again. It'll make more sense. So now we have 42, 83, 99, and 100. This is our new data structure. If we pick a value roughly in the middle, let's say 83, is this equal to 64?
No.
No. Is it greater than or less than?
Greater than.
Right. So we know that this number that we're looking for has to be on this side of the algorithm, right? So we can exclude all of those numbers from consideration. We now have a data structure containing only one number, 42. Is 42 equal to 64? Do we have anywhere left to go? We may therefore conclude it's not in there. So because 42 does not equal 64, return false. Does that make sense? Are there any questions about this? Yeah. So basically, this is a very different way of thinking about searching, right? Because we're not specifically focused on searching the individual elements. We are concerned about a search space, right? What we're doing is we're trying to whittle down the portion of this data structure wherein the answer must lie, right? And using this method of bisection, we can drop half of the data structure, actually at least half of the data structure, at a time, right? So this is an array that had 9 elements, right? We could then chop it down to 4. We chop that down to 1, although that's kind of, sometimes they'll leave the middle one in, but it doesn't really matter. At any rate, in 3 steps, we go from 9 to 1, and then we know whether or not we found our thing or not, right? You can imagine if I had an array that stretched across the whole top of the blackboard, right? It wouldn't take me more lines than that upper line of the blackboard to finish it, right? Add 1 step and you can multiply the maximum that you can process by 2, right? So this is kind of a fancy way. Fancy way of saying that the number of steps that you need here is proportional to the base 2 logarithm of n, right? Now, it's not going to be exactly that every time. Like in this case, what would that be? It would be 2 to the 8 is 4, so it would be like 4 point something. 2 to the 4 is 8? No, 2 to the 3 is 8, pardon me. So it's like 3 point something, and like we end up with 3 exactly rather than like rounding up to the point something or whatever. But, at any rate, so, it's like 2, 4, 8, 16, 32, 64, 128, right? You can get to very, very, very large numbers very quickly using this method. The only trick is that the data has to be sorted. right? Now, sometimes your data is naturally sorted. If the data that you're receiving is being received over a period of time, then the time, and if the thing you're searching for is like timestamps, then it costs you literally nothing to search by time, you can actually search elements by time in this actual runtime. Sometimes, if you want to search, like let's imagine you had a database wherein you had students' grades, right? And you wanted to see if anybody in this class is getting like an 83, right? In order to order that data structure, you would need to spend a lot more than big O of log base 2 on it, right? Like sorting algorithms in general, some of the poor ones, you can kind of think of like an upper limit on a pretty bad sorting algorithm as being big O n squared, right? So if you have to pre-sort the data, this isn't going to give you much. And frankly, if you're going to the trouble of sorting it, you can probably just do linear search and save yourself some time, right? So in particular, the binary search algorithm is most effective for data structures that are already sorted. Like, otherwise you're spending more time sorting it than you are searching it, and vastly more time sorting it than searching it, so that's not necessarily very useful. However, yes? Okay. One thing that you can do is you can have a data structure which maintains a property of sortedness, right? So while it is what am I missing? Come on, lost my train of thought. Terrible time to lose a train of thought. So let's imagine you have an existing data structure, right? Let's imagine that the data that you're interested in is sorted, right? How much does it cost to add one element to that and keep its sortedness property? Yeah. Say again? The number of elements in the list. Well, the amount of time it takes for you to find that element's spot in the data structure, right? So, we have a clever algorithm for finding spots in data structures, right? So, essentially, if you structured your data in such a manner that it maintains the sortedness property so that when you want to find something, you can find something quickly, that's actually less expensive in the long run than allowing your data to become totally disarrayed and then trying to order it on the fly when you need data out of it again, right? So it is possible to create software systems that basically maintain some level of organization that can have very good actual practical runtime benefits, right? But what that requires is it requires structured and controlled access to the data structure. We have mechanisms for providing structured and controlled access to data structures, because if the access was uncontrolled and unstructured, any old Billy Joe could just throw some integers into the middle of your nicely sorted list, and bam, there goes your sortedness property, right? And trust me, the last thing you want to do is trust anyone to do anything properly, as I've found with experience. TAs in this class excluded, because they're awesome. So yeah, the way that we generally control these things is by enforcing what we call a data policy, And the manner in which data policies get enforced, generally speaking, inside of the object-oriented paradigm is by structuring objects. Objects allow you to structure the data, hide the data behind a wall, and basically what an object is you've got like, think about you've got like a medieval town with a wall around it, right? And inside of the town is the data. There's a big gate, and an ornery old man who sort of slides the shutter open and says, "What do you want?" It's like, "I want to give you some data." It's like, "Well, you have to order it first." And then he slides it in. And that's essentially how you can enforce data policies with object-oriented programming, where in that particular metaphor, the town itself is the data, and the gate with the ornery old man is an access method. So, I think that's about as much damage as we can do today. Thank you very much for your time and attention, folks, and we'll see you all on Friday.